big day today, massive day today. That's because today is the first time we're touching loops. Loops allow us to do some of the things that computers are best at doing compared to humans, which is to say, loops allow us to get computers to do things that are repetitive and tedious and otherwise very, very boring for us to do. So this is really awesome. Looping just means repeating some set of actions as long as some Boolean, some true or false condition evaluates to true. Okay, you can see in this flowchart here, we evaluate the condition. If it's true, we do our statements, we go back and we check again. If it's false, we exit. And we do that over and over and over again until that condition terminates. Okay, in order for the loop to terminate, each iteration of the loop has to move the variables closer to satisfying whatever that condition is. So for the while loop, which is the particular structure we're looking at today, we'll start by initializing any variables that we want to use outside of the loop. Then we're going to test whatever condition we'll use to run the loop, and we'll define whatever calculations or whatever changes in the variables happen inside the loop if that condition evaluates to true. Now, this is really important. Whatever variables are involved in the condition, we have to actually change them somehow inside the loop, or we never actually exit the loop. Okay, we have to eventually move the condition toward being false so that we can break out of the loop. We'll talk about two general kinds of while loops, two ways of structuring them. The first is a count-controlled loop. Count-controlled loop. That means just doing something a certain number of times. Doing something until a counter variable reaches a particular value that we have in mind. This is an example of a count-controlled loop. Okay, I want to compute 1 plus 2 plus all the numbers, all the integers between 1 and 100 inclusive. So you can see in our code here, we start by initializing a couple of variables. Sum starts at 0, our counter starts at 0, and the condition we're using as a gate to this loop is making sure that the counter is less than or equal to 100. So as soon as that counter gets bigger than 100, we're going to exit the loop. But until then, we will repeat the statements over and over and over again. You can see that we have an increment statement here, counter plus plus, that actually moves our counter toward breaking this condition. So when we first enter the loop, sum is 0, counter is 0, 0 plus 0 is 0. So that's the sum after the first run of the loop. Then we increment counter, we go back, check our condition. Now counter is 1. Is 1 less than or equal to 100? It is, so we enter the loop. Now, sum plus equals counter. That's 0 plus equals 1. The result is that sum now gets the value of 1. Great. We did the statements in the loop. We added 1 to counter. Now counter is 2. Go back. Check the condition once again. Is 2 less than or equal to 100? It is. So we enter the loop again. Sum. Now sum is 1. Okay, 1 plus equals 2 is going to give me 3. We'll increment counter, go back up to the top and check. Okay, is 3 less than or equal to 100? Perfect. Enter. Keep going ad nauseum until we get to 100. Okay, well, when counter's 100, we come back up to the top, we check our condition. Okay, is 100 less than or equal to 100? It is. So sum is 4950 at that point. We add 100 to it, we get 5050. Then we increment counter one more time. Counter is now 101. We go back to our condition and check. Counter is 101 less than or equal to 100? It is not. So this time, we do not enter the loop. We go to the bottom, print out sum, and the value that gets printed is 5050. If we were now to actually go and print out counter, we would have 101. And that makes sense because we added 1 to counter, and when we got back to the top, we didn't enter the loop, but counter still holds its value. So that's a count-controlled loop. We're saying do this thing 100 times, a certain number of times. Now, a task-controlled loop is slightly different, at least in philosophy. The idea is do something until a certain task is actually accomplished. There's a different feel. It's less about doing something a particular number of times. Here's a great example. Right? We want to find the first number for which 1 plus 2 plus all the integers up to it is greater than 1,000,000. Okay, find the first number that when you add up all the integers from 1 up to that number, the sum is greater than 1,000,000. So we start with a 0 sum, we start with a number 0, and while the sum is less than or equal to 1,000,000, we will add 1 to number and then add number to the sum. Okay, so you can trace through this on your own. The idea is essentially we haven't predefined how many times we're doing something. We don't actually have a proper counter here that is determining our condition's truth. So this Boolean condition actually depends on the task of getting a sum that is greater than 1,000,000. At the end, when we break out of the loop, we'll actually print out numbers. So you can see the two sort of distinct philosophies for making these loops. One is do something a set number of times, and the other is do something until some other condition is satisfied as true. It doesn't necessarily mean do something a particular number of times. Here's another example of a task-controlled loop. I want you to guess the word I'm thinking of. I don't really care how many guesses it takes, and that's not really the condition of the loop. Okay, if I make a scanner object called reader, I got a string named input, and I prompt you for a word. Okay, well, my secret word is spinach. It's not really a secret because you can see it. But in any case, my condition here is while the input that you gave me is not equal to spinach. Okay, as long as that's not true, we go back into the loop. I tell you, nope, try again, and then I prompt you for a new input. Then we go back up to the top, and I check input again. That's a task-controlled loop. Okay, it doesn't have to happen a certain number of times. It just depends on making this condition evaluate to false. Couple ways you can end up with what we call infinite loops, and those are loops that run forever, right? They never actually properly exit the loop. One way is you could have a counter that doesn't actually increase. Right here, we start our counter at 0, and the condition is as long as the counter is less than 100, print out the counter. Well, we forgot to increment the counter, and so this loop is going to keep running forever and ever 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 and ever. That's one way to have an infinite loop. Second way is if the condition itself is just always true. So here, okay, we start with a counter equals 1, and our condition is while the counter is greater than 0. Well, we do have an increment. We are changing our counter, but we're not changing our counter in the direction that matters. If counter starts at 1, and the way we're changing it is by adding 1 to it, well, it's always going to be greater than 0. So even though we're changing our counter, we're changing it in the wrong direction, and this condition will always evaluate to true. That leads, again, to an infinite loop. Here's the Factorial program. You should open this up on your computer, and then you can play with it a little bit. You remember from math that the factorial of a number is the product of all the integers from 1 up to and including that number. So 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, that's what factorial means. So we've got a little program here that takes as an input a number and calculates the factorial of that number using a while loop. Okay, so let's take a look at it real quick. We instantiate a scanner object. We prompt the user for input. We say, okay, make me a variable called number and assign the user's input, an integer, to that value. We'll start with product equals 1 and count equals 1. Product is where we're actually going to keep track of our running product, right? 1 times 2 times 3 times 4, all the way up to whatever our number was. And count is where we're going to keep track of what number we're multiplying right now. So look, our condition is while count is less than or equal to number. So as an example, if I enter 5 factorial, well, count is going to start at 1 and number is going to be 5. So that means while my count, which starts at 1, is less than or equal to 5, I'll say product equals product times count. Okay. I'll print out whatever the product is, and then I'll increment count and do it again. I'll check to see if my count is still less than or equal to my number. Once we actually get to the number that the user entered and exceed it, once we get bigger than that number, we'll break out of the loop and print our result. So let's run this. Let's try it with factorial of 3. So 3 factorial. We expect this to be 1 times 2 times 3, which is 6. Great, and it looks like that's exactly right. The factorial of 3 is 6. So this variable that's being printed at every step is the running product. Let's try it one more time, this time with a bigger number. So let's try 20 factorial. Wow, 20 factorial got really big. And in fact, it got so big that we ended up with an arithmetic overflow error. Okay, you remember that. That means the value got too big for a 32-bit int to hold. So we got these goofy negative values. Got to be really careful. What if I wanted to modify this so that it printed not just the running product, but the count as well? So let's see. Let's go to this print statement inside the loop, and let's add in some language printing in the counter as well. So now I've added count and then 2 tabs and then product. So let's run this again. I'll clear my screen, save my code, click run, enter a number greater than 0. Let's try 7 factorial. Well, look, now I've got my counter printed and I've got that running product. And 7 factorial, it looks like, is 5040. So open that up in Eclipse, play with a little bit, see what happens if you change some things in the loop. So before you close up shop, here are the things you want to be able to do. First, you want to be able to write a simple while loop. Okay, you're going to practice that a lot on the problem set 2 exercises and, of course, in problem set 2 itself. Go ahead, open, run, and examine the Factorial code, which is posted on the class website. Make sure you can differentiate between the idea of a task-controlled loop and a count-controlled loop. Where a count-controlled loop is something that we do a certain specified number of times. A task-controlled loop is something that we do until a particular condition is satisfied, independent of how many times it takes. Just like we did with that very first count-controlled loop, you want to make sure that you can trace the action of loops with a chart, maybe by recording the value of a particular variable at every step of the way. And we want to know why some loops end up being infinite loops. Okay, and some key reasons for that are maybe we forgot to increment or decrement a counter. Or maybe we are changing a counter, but we're changing it in the wrong direction. Those are some good things to brush up on before next class. Have a great night.